Hello, so this is the video for 2.2 and 2.3, which is trends across the periodic table. Now we have covered this in class on Monday, but I think it may be a good idea to quickly revise just in case anyone need a quick catch up. And I think at least one person was away on Monday, so this will benefit that person. Now, essentially, we started by looking at a few concepts. So in this case, we looked at core charge and distance from the nucleus. And I think I'm going to divide this video into multiple parts. So this is the first part that is just going to talk about the attractions between the nucleus and the valence electrons a little bit. All right. Um, well, I think what I'm going to do is I'm just going to go through every slide. Obviously, if you want to write anything down, you may have to pause the video. I'm not going to leave that much time, otherwise I'd be here until the end of time, I think. Okay, so I think I want to point out mainly is that whatever we're learning right now, so the concept of core charge or number of electron shells, this is just a model. So this is a way that we came up with in order to explain the trends in the attraction between the nucleus and the valence electrons. This is not the only model you are going to encounter if you continue studying chemistry in the future, but it is the one that we're going to stick with in year 11. Okay, so according to this model, the attraction or the attractive force between the nucleus and the valence electrons are influenced by two factors. We have core charge and the number of electron shell. So this is a model. I just want to point that out. And the difference between a model and reality is a model only reflects certain aspects of reality, and it will always have limitations. And I think a lot of you have actually discovered the limitation of this model, at least in the context of core charge, is that it's intuitively pretty difficult to actually imagine and to actually understand why core charge increases. But I think for now we're just going to have to accept that. I may potentially go into an explanation next week, just to talk about electron shielding a little bit in order to help you understand the concept of core charge a little bit better. Anyway, again, this is a measure. I need to really emphasize this. It's a measure of the attractiveness. It is by no means the only way to represent the attractive force. But again, it's just a representation. It is not the attractive force itself. It is a translation of the attractive force. And the way that we measure core charge is, well, I'm just going to go through this example again. If you have a lithium atom, and I guess you can say that a lithium atom actually has 3 protons in the nucleus in the middle here. But the way that it works is there are these two electrons, these two inner electrons that will potentially shield the valence electrons from the nucleus. So the valence electron is not going to feel the attractive force of 3 plus because of the shielding. And effectively, if you cancel all the inner shell electrons, the attractive force that the valence electron can feel in the case of lithium will be just 1 proton left. So it's equivalent to around +1. And this is considered the core charge. Once again, it's just a representation of the attractive force. It is by no means the only thing that influences this attractive force. So one way to calculate core charge is the number of protons minus the number of inner shell electrons, and obviously this also equal to the number of valence electron, given that we have a neutral atom. So number of valence electrons in a neutral atom. So just very quickly, I don't think I actually went through this example, but we did something similar in class. In the case of magnesium, the core charge will be +2. For aluminium, will be +3, and then I think that's +7. I'm just looking at the number of valence electrons in the in a neutral atom of this element. So that will be a measure of core charge. But looking at these numbers alone, I wouldn't say that, say for example, oxygen has a higher attraction between the nucleus and the valence electrons compared to aluminium. I do need to look at the number of shells as well. Okay, that was not well planned. Let's try again. So aluminium is +3 and oxygen is +6. Okay, so the higher the core charge, the more attracted the valence electrons are towards the nucleus, given that they have the same number of shells. I think it's very important to emphasize this point. Unless the number of shells are the same, you can't really use core charge as a direct measurement of the attractive force between the valence electrons and the nucleus. Same number of electron shell. Okay, so which it brings us to this statement, which I asked the class, if the core charge remains the same, would the attractive force between valence electrons towards the nucleus remain the same? And if you look at the visual representation of, say, sodium, this is using the shell model, and compare it to francium. Now the core charge in both cases, so the core charge here is +1, and the core charge here is also +1. So if you consider both cases, they do have the same core charge, and the only difference is the number of electron shells. And having more electron shells is going to increase the distance between the nucleus and the valence electron, and that would decrease the attractive force between them. I mean, it's simply a matter of distance. If they are further away from each other, then it's harder to feel the same attractive force. Distance is actually very important when you have an attraction. Chemistry speaking anyway, I'm not going to generalize too much, but in the case of chemistry, you kind of need to be fairly close to each other to be considered to have an appreciable amount of attraction between each other. I could have so many examples inserted here, but I'm going to move on. So the second thing that will affect the attractiveness or the attraction between the nucleus and the valence electrons would be the number of occupied shells. And simply, if you have more occupied shells and you increase the distance between the nucleus and the valence electrons, you will decrease the attractive force. Okay, so I think, okay, so this is just another visual representation of an increase in distance by increasing the number of shells. And even if you have the same core charge as represented by the same number of valence electrons in this diagram, you still have a decrease in the attractive force as the distance gets larger. Okay, so question 1, once again, we did this in class. You need to predict and explain the trend. Not sure why there's an earth here. So the trend in attractions between the nucleus and the valence electrons down a group. Now, this is a 2-mark question, so you need to predict and then you need to explain. And as always, if the question asks you to explain the attraction between the nucleus and the valence electrons, you need to mention both core charge and the number of electron shells in your answer. I mean, this visual representation is just a way to show you the different factors that you need to consider when you answer this question. So I always start with the direction. The direction that we're looking at in this question is down a group, and you need to know what the members of the same group have in common and what changes when you go down a group. The same can be said for going across a period. Anyway, when we go down a group, elements have the same number of valence electrons. That's what elements in the same group have in common, but they will have increasing number of occupied shells. So if you recall the example that we just did before, especially that visual representation, this visual representation, this is an example of members of the same group. As you go down the different periods, this is going to be all in group 1. And you can definitely see that as you go down the group, the number of shells increases, why core charge doesn't change. Okay, so if core charge doesn't change, then any variation in the attractive force between the nucleus and the valence electrons is not going to be due to core charge. It's going to be due to the increasing number of occupied shells. Another thing to keep in mind is that you can only make a comparison based on the number of occupied shells if you already know that the core charge is constant. Otherwise, it's a little bit hard to make a comparison. So if you have an increasing number of occupied shells, the distance between the nucleus and the valence electrons would increase, which means that the attraction that the valence electrons feel towards the nucleus would decrease as a result of that. So we look at the full answer. Make sure you specify direction. So specify a direction. And make sure elements have the same core charge. So I have mentioned core charge, and I've also talked about the number of occupied shells, and then the actual reason why there is a change in the attraction. So that would be my explanation. It seems like a lot, but this wouldn't give you more than maybe 1 mark and maybe 2 at most. And then we have the prediction, decrease of the attraction between the nucleus. So decrease the attraction between nucleus and valence electrons. If you ever run out of time in an assessment, it is a good idea to at least make a prediction. Hopefully you have some time to think about your prediction at least. Similarly, we have question 2. Now, since we already did this question in class, I'm not gonna, well, this is a 2-minute timer. Obviously, I do encourage all of you, if you haven't done this question, to pause the video and try to do it yourself before I talk about the answer. But I'm just go ahead to the answer immediately. And once again, we're talking about going across the period. This is probably optional, but it is a good idea to specify that you're going from left to right, or you probably get away with just drawing an arrow. Now, when you go across a period, the number of valence electrons increase. That's what varies when you go across a period. You start with 1 valence electron and you go all the way towards 8 valence electrons in the p shell. There could be a case when you have all the subshells in there as well. But elements in the same period have to occupy the same number of shells. That is just what elements in the same period have in common, which means that the distance between the nucleus and the valence electrons will not be the same. However, they have the same number of occupied shells, so you probably cannot make a call by looking at the number of occupied shells. It's going to be the valence electron. So if there is an increase in the number of valence electrons, that will increase core charge, which would increase the attraction between the nucleus and the valence electrons. So once again, we have the full answer. Specify the direction for me. So let's say going across a period from left to right, just to be very clear with our answer. The number of electron shells remain the same. So I've talked about the number of shells, and I've talked about core charge. Core charge would increase, and this would increase the attraction between the nucleus and the valence electron. So this is a little bit shorter than the other answer down a group, because you don't have to talk about the distance between the nucleus and the valence electron. Okay, so just to recap, as you go down a group, the attraction between the nucleus and the valence electrons will decrease because you have more shells and you increase the distance between the nucleus and the valence electron. Why the core charge doesn't change. If you go across the period from left to right, the attraction will increase as you have increasing core charge with the same number of occupied shells. So this attraction increases across the period and decreases down a group. And this is going to govern every other property that we're going to discuss after this, which are these. So this is the end of the first part of the videos. Do I want to keep the ink annotation? Mom? I need to stop the video.